What if our solar system's greatest discovery has yet to be made? How could a giant planet hide in the icy darkness far beyond Neptune? Dear traveler, welcome. Today we're off to the frontiers of our solar system, where the sun is but a distant sliver in the dark immensity. In these icy, enigmatic lands, astronomers peer into the invisible, in search of the mysterious Planet X. But before you set off on your next adventure, remember to like the video and subscribe to the channel, so you don't miss a thing. Thanks, and have a great trip! The classical solar system as we know it is made up of 8 main planets orbiting our star, the Sun. Each of these planets has unique characteristics that make them fascinating worlds, from rocky planets close to the Sun to distant gas giants. Let's start with the 4 telluric planets closest to the Sun: Mercury, Venus, Earth, and Mars. These planets are characterized by solid rocky surfaces and relatively thin atmospheres, except for Venus, which has an extremely dense atmosphere. Earth, of course, is the only planet known to harbor life, and Mars, often referred to as the Red Planet, continues to captivate attention with its traces of water and ancient habitable conditions. Beyond the asteroid belt, we enter the region of the gas giants with Jupiter and Saturn. Jupiter, the largest planet in the solar system, is a massive ball of gas, mainly hydrogen and helium, and boasts an impressive series of moons, some of which, like Europa, could potentially harbor oceans beneath their icy surfaces. Saturn, with its famous rings, is equally impressive, and continues to be studied to understand the formation of planetary systems. Finally, we have the ice giants Uranus and Neptune, located at the very edge of the solar system. Uranus is unique for its tilted axis of rotation, while Neptune, the furthest planet from the Sun, is known for its violent winds and massive storms. Neptune marks the limit of the classical solar system, beyond which begins a largely unexplored territory. Just beyond Neptune lies the Kuiper Belt, a region populated by icy bodies, asteroids, and dwarf planets like Pluto. Although Pluto was downgraded from planet status in 2006, it remains an object of great scientific importance. This region probably contains thousands of similar objects, remnants of the early stages of the solar system's formation. The Kuiper Belt thus represents a frontier zone where the limits of our understanding dissipate, leaving room for even greater mysteries, such as the hypothetical Planet 9, also known as Planet X, which could be lurking beyond Neptune. The discovery of Neptune in 1846 marked an essential milestone in the history of astronomy, and played a key role in the way we search today for unknown celestial bodies such as Planet 9. This discovery was particularly remarkable because it was not the result of direct observation, but of a series of mathematical calculations based on the laws of gravitation. For millennia, the only planets known to humans were those visible to the naked eye, or through simple telescopes: Mercury, Venus, Mars, Jupiter, and Saturn. These luminous worlds, easy to spot in the sky, made up our entire planetary universe. But in 1781, astronomer Sir William Herschel turned this vision on its head when he discovered the 7th planet in the solar system, an icy blue. At first, it was thought to be a star, as it shone so faintly in the sky. But after closer observation, it was realized that it was indeed a planet, located at an extraordinary distance of more than 19 times that which separates the Earth from the Sun. This planet was named Uranus, and its distance is such that it takes 84 years to complete a single orbit around our star. Herschel not only discovered Uranus, he also revealed many other celestial wonders, such as double stars and nebulae. But the adventure didn't stop there. In the mid-19th century, astronomers soon noticed something disturbing. Uranus's orbit didn't seem quite right. A mysterious force seemed to be disturbing it, imperceptibly tugging at the planet. Scientists concluded that there must be another massive body in this remote region of the solar system, so they turned to mathematics to solve the mystery. Two astronomers, John Couch Adams and Urbain Le Verrier, working independently of each other, set out to solve this enigma through complex mathematical calculations. Le Verrier, in particular, analyzed the perturbations observed in the orbit of Uranus and used Newton's gravitational equations to predict the possible location of an unknown massive planet. In 1846, based on Le Verrier's calculations, German astronomer Johann Galle pointed his telescope at the indicated zone and discovered Neptune, just 1 degree from the predicted location, a planet so distant and so dimly lit by the sun that it was invisible to the naked eye. This revolutionary discovery changed astronomers' perception of how to discover new celestial bodies. It proved that objects invisible to the naked eye could be detected thanks to their gravitational effects on other known bodies. If we had been able to discover Uranus and Neptune using mathematics and telescopes alone, how many other hidden worlds were still waiting to be discovered, lurking in the distant darkness of our solar system? In the 19th century, the discovery of Neptune thanks to gravitational calculations marked a turning point in the history of astronomy. However, no sooner had this new planet been identified than astronomers began to ask new questions. The perturbations observed in the orbit of Uranus were not entirely resolved by the presence of Neptune, suggesting that something even more massive was influencing these mysterious trajectories. This idea gave rise to the theory of an as-yet unknown planet beyond Neptune, dubbed Planet X. This conclusion was confirmed after Voyager 2 passed close to Neptune in 1989. This space probe established that what was thought to be an influence on the orbit of Uranus was in fact due to an erroneous assessment of Neptune's mass. Attempts to discover planets beyond Neptune date back long before the discovery of Pluto, and were often based on indirect observations such as perturbations in the orbits of other objects. In 1880, an astronomer named George Forbes hypothesized the existence of 2 trans-Neptunian planets. He thought that one of them would be located 100 times the distance between the Earth and the Sun, i.e., around 15 billion kilometers or 9.3 billion miles, while the other would be 300 times that distance. According to Forbes, these planets would be responsible for aligning the orbits of certain comets, in much the same way as comets passing close to Jupiter tend to group their orbits around the planet. The idea is very similar to modern Planet 9 theories, which explain that the orbits of certain distant objects are influenced by a large, as-yet undetected planet. One of the first to take a serious look at this hypothesis was American astronomer Percival Lowell in the early 20th century. Fascinated by the idea of an unexplored solar system, Lowell undertook an extensive search for this hypothetical planet. In 1894, he founded the Flagstaff Observatory in Arizona, specifically dedicated to this quest. For years, Lowell and his team scanned the skies, hoping to detect a trace of this massive object. They believed that a giant planet, located well beyond Neptune, could explain the gravitational anomalies observed. In his quest to locate this mysterious object, Lowell systematically began his search in 1906. After long and complex astronomical calculations, Lowell succeeded in predicting the potential orbit and position of a hypothetical celestial body, which he named Planet X. This name, Planet X, had already been used by the French mathematician Gabriel Delay, who had also suggested the existence of a trans-Neptunian planet due to disturbances observed in the motion of Uranus and Neptune. Despite his efforts and a certain enthusiasm for Planet X, concrete results were slow in coming, and Lowell never saw his hypotheses confirmed in his lifetime. His research led to a real mystery, which would only be partially solved after his death. In 1930, astronomer Clyde Tombaugh discovered Pluto at the Flagstaff Observatory, exactly in the zone where Lowell had predicted the presence of Planet X. For several decades, Pluto was recognized as the 9th planet in the solar system. Its small size and eccentric orbit were not yet well understood, but the scientific enthusiasm surrounding this new planet masked these anomalies. Over the decades, however, more detailed studies revealed that Pluto was much smaller than expected. With a diameter of around 2,400 kilometers or 1,500 miles, it was not even larger than some of the moons of Jupiter or Saturn. What's more, observations and gravitational calculations showed that Pluto was far too small to explain the gravitational anomalies detected on Uranus and Neptune. In other words, it couldn't be the imposing Planet X that Lowell had imagined. Pluto's status was further called into question at the beginning of the 21st century, as astronomers discovered new similar objects in the Kuiper Belt, a region beyond Neptune populated by small icy bodies. In 2005, the discovery of Eris, an object even more massive than Pluto, forced the scientific community to rethink the definition of a planet. In 2006, the International Astronomical Union reevaluated the classification of planets in the light of the growing number of discoveries. It introduced 3 criteria that a celestial object had to meet to be considered a planet. It had to orbit the Sun, be massive enough to have a spherical shape, and have cleared its orbital neighborhood of other debris. Pluto didn't meet this last criterion, as its orbit crosses that of Neptune and it shares its region with other similar objects. As a result, Pluto was downgraded to dwarf planet status in 2006, losing its title of 9th planet. This decision, though controversial, paved the way for a better understanding of the diversity of objects beyond Neptune. This has rekindled the quest for a true Planet X, which could be lurking even deeper in the unexplored depths of our solar system. For several decades, astronomers have been observing disturbing anomalies in the orbits of trans-Neptunian objects, small icy bodies located beyond Neptune in the Kuiper Belt. These objects, though diverse in size and composition, seem to share a strange commonality. Their orbits are often eccentric and inexplicably aligned. This observation has led some scientists to speculate that a massive, as yet undetected body may be exerting a gravitational influence on them. One of the most intriguing anomalies concerns the clustering of orbits of very distant trans-Neptunian objects, such as Sedna and 2012 VP-113, which have highly elongated trajectories. In theory, these objects should be more randomly distributed in space, yet their orbital alignment suggests the existence of a powerful gravitational body disrupting their motions. In 2016, a surprising theoretical discovery transformed the idea of Planet 9, once relegated to science fiction, into a captivating scientific hypothesis. Two researchers from the California Institute of Technology, Konstantin Batygin and Mike Brown, captivated the scientific community with solid evidence based on mathematical modeling. By studying the unusual orbits of several objects in the Kuiper Belt, they have highlighted the possible existence of a massive body, possibly a new planet. According to their calculations, this theoretical planet could solve many of the unsolved mysteries of the solar system. What's more, its nature would correspond perfectly to a type of planet regularly observed in other star systems across the galaxy. However, the journey has not been an easy one. Sedna's discovery in 2003 intrigued scientists, as its orbit is very distant and cannot be explained by the influence of known planets such as Neptune. With its closest point to the Sun, or perihelion, at 76 astronomical units, much further away than Neptune's orbit, researchers hypothesized that an unknown massive body might be responsible for this strange orbit. Several theories have been put forward, including the idea that an as-yet undetected planet, a former companion of the Sun, or a passing star could have disrupted Sedna's orbit. In 2014, the discovery of another object similar to Sedna, named 2012 VP113, reignited these speculations. The two objects had similar detached orbits, prompting some astronomers to hypothesize the existence of a massive planet, a super-Earth, located far out in the solar system. At a conference in 2012, astronomer Rodney Gomes suggested that an undetected planet located around 1,500 astronomical units from the Sun, with a highly eccentric and inclined orbit, could be responsible for the orbits of some extreme trans-Neptunian objects. This planet would exert a gravitational influence, causing oscillations in the orbits of these objects. Later, other astronomers such as Chad Trujillo and Scott Shepard also observed that 13 trans-Neptunian objects shared similar orbital characteristics. They proposed that an unknown planet located between 200 and 300 astronomical units could be responsible. Some researchers have even suggested that there could be two massive planets in orbital resonance to explain these disturbances. These hypotheses are still being researched and analyzed. Mike Brown, initially skeptical, nevertheless found the hypothesis interesting enough to share it with Batygin. Together they embarked on an intensive 18-month collaboration to study these distant objects. Their aim was to prove that the idea of a planet was far-fetched and to disprove what they believed to be a myth. The duo, consisting of an observer like Brown and a theorist like Batygin, brought complementary perspectives to the table. Brown relied on concrete astronomical observations, while Batygin used physics to predict how the solar system should behave. This dual approach soon led to a fascinating discovery. The 6 most distant trans-Neptunian objects, including Sedna, all followed highly elongated elliptical orbits. What was even more surprising was that these orbits were not randomly arranged. They seemed to be aligned, as if influenced by an invisible force pointing in the same direction. A far from typical behavior, which ran counter to expectations for classical Keplerian orbits. The orbits of trans-Neptunian objects are supposed to have a farthest point that changes position with each revolution. What makes the situation even more surprising is that these orbits move at different speeds, similar to 6 hands on a clock, each turning at a different rate. It would be extremely unlikely for all these orbits to end up aligned in a similar direction. According to calculations, such an alignment could occur only once in 100 times, which, while not totally impossible, raises serious questions. What particularly surprised the researchers was that the orbits of the 6 trans-Neptunian objects are also inclined to the plane of the ecliptic by around 30 degrees. The probability of such a coincidence with such close inclination angles and orientations is about 1 in several 100,000. This discovery suggested to the researchers that this was no coincidence, but that a significant force must be influencing the orbits of these distant bodies. Initially, Mike Brown and Konstantin Batygin considered the possibility that the combined gravity of a group of objects in the Kuiper Belt might influence these orbits. However, this hypothesis was soon abandoned, as it would imply the existence of a Kuiper Belt some 100 times more massive than it is today. Faced with this impasse, the researchers turned to a model involving a hypothetical planet supposed to interact gravitationally with the 6 trans-Neptunian objects. Although this simulation showed results close to the observations, it did not fully explain all the observed features. Later, they tested a configuration where a more massive planet with an orbit oriented in the opposite direction to that of the 6 objects better reproduced the observations. However, this configuration raised a problem of long-term stability. Such a planet could destabilize the orbits of the icy planets or collide with them. To refine their model, Mike Brown and Konstantin Batygin decided to introduce orbital resonances. Their hypothesis was that the 6 trans-Neptunian objects could have orbits synchronized with that of the hypothetical planet. For example, for every 4 complete revolutions of the planet, Sedna would make exactly 9, illustrating a phenomenon similar to the orbital resonances observed between Jupiter's satellites or between Neptune and Pluto, which prevent their collisions. The mathematical model developed by the researchers not only explained the existing observations, but also predicted the direction of this hypothetical planet's orbit, an essential detail for its future discovery. Even so, Brown and Batygin remained cautious. Brown recalls that although the idea seemed plausible and promising, it was still unproven. For a hypothesis to become a solid theory, it had to make testable predictions, confirmed by concrete observations. The researchers scrutinized their model for such a prediction. They discovered that if this planet really existed, it would have to influence objects whose orbits were inclined almost perpendicularly to the ecliptic plane, i.e., at around 90 degrees. However, no objects with such orbits had yet been observed, which was an obstacle to their hypothesis. However, they realized that their earlier observations were based on a limited data set, focusing only on highly elongated orbits and excluding smaller objects that could cross Neptune's orbit, as these were thought to be unstable. On re-evaluating their data, they discovered 5 new celestial bodies whose orbits corresponded precisely to what their model had predicted. These objects were located exactly where the presence of Planet 9 was expected. Later, 4 other objects with orbital characteristics similar to those of Sedna were also discovered, again confirming the model. Thus, what had begun as a tantalizing hypothesis was increasingly taking shape, strongly suggesting that there may well be something massive hidden in the outer reaches of the solar system. If discovered, Planet 9 would become the 5th largest planet in our solar system, and would be around 10 times more massive than Earth, with a radius of 2 to 4 times greater. These impressive figures would place it directly after Neptune in terms of size, although its mass puts it in a unique category among known planets. What's more, this would place it in an intermediate category between terrestrial planets and ice giants like Uranus and Neptune. Unlike rocky planets such as Earth or Mars, Planet 9 would probably be gaseous, like Uranus and Neptune, its big sisters in the outer solar system. These hypotheses about its gaseous nature are based on similarities in the formation of planetary systems, suggesting that a planet of this size would have accumulated a large quantity of gas during its formation. According to astronomer Mike Brown, if it exists, its mass would be sufficient to have cleaned out its orbit, i.e., ejected or captured nearby large bodies, over the 4.5 billion years of the solar system's existence. What's more, its gravitational force would dominate the outer region of the solar system, which according to the current definition of a planet would classify it well as a planet. So, if this planet is discovered, it would meet all the criteria to be officially recognized as a planet. As for its atmosphere and surface conditions, Planet 9 would probably be an icy planet, similar to the solar system's ice giants like Uranus and Neptune. Its composition could include elements such as hydrogen, helium, and ices of water, ammonia, and methane. Temperatures on such a planet would be extremely low, given its distance from the Sun. The atmosphere would probably be dense, with deep layers of ice clouds and perhaps storms equivalent to those seen on Neptune and Uranus. Surface temperatures could drop to very low levels, well below zero, with conditions that would be anything but hospitable for life forms as we know them. Atmospheric winds and currents could be intense, and atmospheric pressure could be high due to the planet's large mass. Studies of icy objects in the Kuiper Belt, as well as planets like Neptune and Uranus, help us to formulate these hypotheses about the surface conditions and atmosphere of Planet 9. The most fascinating feature of Planet 9 is its supposed orbit. The initial hypothesis concerning Planet 9 suggests that it follows a highly elongated, i.e. elliptical orbit around the Sun. Its eccentricity, i.e. the extent to which its orbit is stretched, could be between 0.2 and 0.5. This means that the planet is sometimes very far from the Sun, and at other times much closer. Planet 9's average distance from the Sun is estimated at between 60 and 120 billion kilometers, or between 37 and 75 billion miles, or 13 to 26 times Neptune's distance. To put this in perspective, Neptune, which is already around 4.5 billion kilometers, or 2.8 billion miles from the Sun, seems close by comparison. This distance would make Planet 9 an inhabitant of the farthest reaches of the solar system. With such a wide orbit, it would take about 10,000 and 20,000 years for it to complete a full orbit around the Sun, meaning that since the appearance of the first human civilizations, Planet 9 would not yet have completed a single full revolution around our star. What's more, its orbit would be inclined between 15 degrees and 25 degrees to the plane in which the Earth and other planets revolve around the Sun. The furthest point of Planet 9's orbit, called aphelion, would be in the direction of the constellation Taurus. On the other hand, its closest point to the Sun, or perihelion, would be in the regions of the constellation Snake, Ophiuchus, and Libra. Such an orbit suggests an extremely elongated trajectory, implying that Planet 9 would spend most of its time far from the Sun, in the darkest and coldest regions of the solar system. Its proximity to the Sun as it approaches could occur at an extremely great distance, which would have an impact on Trans-Neptunian objects and the dynamics of the outer solar system. If such a planet exists, it would gravitationally dominate a much larger region of the solar system than any other planet. Its influence could extend over hundreds of billions of kilometers, disrupting the orbits of the small icy bodies that populate the outer reaches of the solar system, such as the Trans-Neptunian Objects. This gravitational dominance, which extends well beyond Neptune's orbit, could explain many of the anomalies observed in the trajectories of these distant objects. If the existence of Planet 9 is confirmed, sending a probe to explore it could take decades or even centuries with current technologies. For example, even if the James Webb Space Telescope discovered this planet and a space mission was immediately planned, it would take at least 10 years of preparation before a probe could be launched, so not before 2034. If this probe were to reach Voyager 1's record speed of 17 kilometers per second, or 11 miles per second, and Planet 9 were at its closest point to the Sun, or perihelion, it would take around 57 years to cover the 30 billion kilometers separating it from the Earth. This would mean that a flyby of the planet would not take place until 2085. But if the planet is at its furthest point from the Sun, or aphelion, as might be the case with an orbit of 10,000 to 20,000 years, it would take around 343 years for a probe to reach its destination. However, there are alternative technologies that could speed up this process. For example, miniature probes equipped with solar sails, such as those envisaged by the Breakthrough Starshot project, could enable a faster flyby and return of images in much less time. What's more, recent research suggests that Planet 9 could be closer to the Sun than originally thought, with an orbit of 7,400 years and a mass 5 to 6 times that of Earth. If it is closer, this would make it brighter and therefore easier to detect. Sky maps have been produced to indicate areas where this planet could be hiding, facilitating future searches. In the search for the mysterious Planet 9, several hypotheses about its origin have been put forward. One of the earliest theories, proposed by Batygin and Brown, suggests that the planet formed closer to the Sun. However, in the course of its evolution, it would have been expelled into a very distant eccentric orbit, after an encounter with Jupiter or Saturn, when the solar system was still in the process of forming. The gravity of a nearby star, or the gaseous residue of the solar nebula, would then have stabilized this distant orbit. Interestingly, had Planet 9 not been hurled so far, it would probably have continued to accumulate matter and become a gas giant like Jupiter or Saturn. But this premature expulsion halted its growth, leaving it smaller than Uranus or Neptune. Another theory is based on the idea that Planet 9 could have been captured in its current orbit by gravitational forces. For example, by crossing a planetesimal disk, which contains small solid bodies formed from the remains of the solar nebula, the planet's speed in orbit would have been modified. This phenomenon would have stabilized its orbit, leaving it on a trajectory similar to the one it has today. Other scientists consider the possibility that a star passing close to the solar system could have disrupted the orbit of an already distant planet, transforming its circular orbit into a more elliptical trajectory, like that assumed for Planet 9. Finally, some researchers go even further, wondering whether Planet 9 might not have been captured from another solar system. If the Sun had encountered another star with planets around it, it's possible that one of these planets could have been torn from its original system and adopted by our own. This scenario is unlikely, but is still possible, especially if the Sun had at some point a binary companion, i.e. a twin star. These theories offer fascinating clues as to how such a distant planet could exist at the very edge of our solar system. However, these fascinating hypotheses remain theoretical for the time being. No direct observations of Planet 9 have yet been made, but the researchers defending its existence are not basing their arguments on mere conjecture. Their work relies on advanced mathematical modeling and computer simulations that take into account the anomalies observed in the orbits of Trans-Neptunian objects. These techniques are powerful tools in modern astronomy, enabling precise predictions to be made from limited data. Mapping dead zones is an essential aspect of the search for Planet 9, enabling astronomers to focus their efforts on regions of the sky where its presence is more likely. These zones are areas of the sky where, thanks to accumulated observations and data collected by telescopes, Planet 9 is unlikely to be found, enabling certain parts of space to be eliminated and the search field narrowed. The quest to discover the mysterious Planet 9 has driven astronomers to use the most sophisticated instruments at their disposal. Among these tools, one of the most important is the Subaru telescope, located on the summit of Mauna Kea in Hawaii. One of the largest and most powerful telescopes in the world, it plays a central role in the search for this hypothetical planet. With its primary mirror measuring 8.2 meters or 27 feet in diameter, the Subaru telescope offers unrivaled observing capacity to peer into the farthest reaches of the solar system, where Planet 9 is believed to be hiding. The Subaru telescope is particularly well equipped for this task, thanks to its cutting-edge technology. It is capable of capturing highly detailed images and examining vast swaths of the sky in a single pass. This is essential in the hunt for Planet 9, as it is extremely difficult to spot it directly. Astronomers have to look for subtle clues, such as the faint movements of Trans-Neptunian objects, to try and locate this hidden planet. With its ability to observe large areas of the sky, Subaru offers a chance to spot those faint gravitational disturbances that could betray the presence of Planet 9. Another key aspect of the Subaru telescope is its ability to operate in infrared wavelengths, which are essential for detecting distant cold objects like Planet 9. At such a great distance from the Sun, the hypothetical planet would reflect very little visible light, making it extremely difficult to detect with the naked eye. However, it would emit a small amount of infrared radiation due to the internal heat it has retained since its formation. It is this radiation that the instruments of the Subaru telescope are able to capture, increasing the chances of detecting Planet 9. The choice of Mauna Kea as the site for this telescope is not insignificant either. The site is one of the best in the world for astronomical observation, thanks to its altitude, low humidity, and low light pollution. These conditions offer exceptional clarity for observations, which is essential for long-term research into objects as distant as Planet 9. But the Subaru telescope is not alone in this quest. Other instruments, such as the Very Large Telescope, or VLT in Chile, and the James Webb Space Telescope can also be mobilized to scan the skies in search of this elusive planet. The James Webb Space Telescope, Hubble's successor, has the technical skills to capture images of such a distant planet, even if these images are limited to a few pixels. Moreover, the search for Planet 9 relies heavily on modern sky scanning technologies, which enable astronomers to observe remote regions of space with unprecedented precision. These observation programs use a variety of telescopes, from traditional optical telescopes to sophisticated instruments operating at infrared and even radio wavelengths. One of the most important surveys in this research is the Wide Field Infrared Survey Explorer, or WISE, a NASA space telescope launched in 2009. WISE scanned the entire sky in infrared wavelengths, enabling the detection of objects that would not be visible in the visible light spectrum. This is an interesting approach, as distant objects such as Planet 9 emit very little visible light, but can be spotted thanks to the faint heat they give off in the form of infrared radiation. Although WISE has not directly detected Planet 9, it has helped to rule out a large number of possible locations, sharpening the areas to be explored. Another key program in this mapping effort is the PAN-STARRS, or Panoramic Survey Telescope and Rapid Response System, a set of telescopes in Hawaii designed to observe the sky at high resolution and over large areas. In fact, PAN-STARRS is particularly effective at detecting the subtle movements of Trans-Neptunian objects, small celestial bodies that could indicate the presence of Planet 9 through their disturbed orbits. Thanks to its powerful optical capabilities, PAN-STARRS can regularly monitor remote areas of the solar system, providing valuable clues for researchers. There are also ground-based surveys. In this context, the Large Synoptic Survey Telescope, or LSST, named Vera C. Rubin Observatory, is an ambitious project set to become one of the most powerful tools for exploring the sky. With a mirror measuring 8.4 meters or 28 feet in diameter, and a camera with 3.2 billion pixels, LSST will be able to capture images of large swaths of the sky with unprecedented sensitivity. Its aim is to map the entire sky every few days, offering dynamic tracking of moving objects, including those at the very edge of the solar system. These technologies are not limited to optical and infrared telescopes. Radio observations, although less widely used in the search for Planet 9, can also provide valuable information about distant objects. By detecting natural radio emissions from certain electromagnetic interactions in space, these instruments can pinpoint objects that escape other detection methods. But the impressive technological advances in astronomy are insufficient, and the search for Planet 9 remains extremely difficult. Several factors contribute to the complexity of this quest, underlining the current limitations of the tools at our disposal. First of all, Planet 9 would be located at an enormous distance from the Sun, probably between 400 and 800 astronomical units, or hundreds of billions of kilometers from Earth. At this distance, the Sun's light reaching the planet is extremely weak, making it almost invisible to traditional optical telescopes. Even the largest terrestrial telescopes have difficulty detecting objects this far away, as the light reflected by the planet would be too weak to be clearly observed in the visible spectrum. Secondly, Planet 9 would have a highly eccentric and elongated orbit, meaning it could spend much of its time at even greater distances from the Sun, beyond the range of our most powerful instruments. As this orbit would take between 10,000 and 20,000 years to complete, the planet's exact position is difficult to predict. Even with advanced mathematical models, astronomers still have to scan huge areas of the sky to hope to detect it. Finally, observations in infrared and optical wavelengths are limited by sky coverage and observing conditions. Infrared telescopes such as WISE are effective at detecting cold, distant objects, but their resolution and ability to detect at very great distances are still in need of improvement. Ground-based observation programs such as Pan-STARRS or the Subaru telescope, although extremely powerful, are influenced by atmospheric conditions, light pollution, and the need to prioritize other celestial objects. These technical limitations show just how complex it is to spot an object as distant and faint as Planet 9, even with today's most advanced astronomical tools. By combining the Subaru's observations with other telescopes, astronomers were able to draw up a map of locations where they found no sign of a celestial body massive enough to be the famous hypothetical planet. This collaboration has eliminated around 78% of the likely areas where Planet 9 could be hiding. Despite this progress, a vast region of space remains unexplored. One of the main difficulties in mapping these dead zones is that Planet 9's eccentric, elongated orbits could temporarily place it at such distant distances that even the most powerful telescopes cannot detect it. Also, certain areas of the sky are difficult to access due to the Earth's position and atmospheric conditions. By progressively eliminating the regions of space where it is not found, astronomers can concentrate their efforts on the regions where its discovery could finally take place, thus tightening the noose around this hypothetical planet. Theories on the existence of Planet 9 are based on the observation of certain gravitational anomalies in the trajectories of trans-Neptunian objects. However, this hypothesis is not the only one in play. Other alternative scenarios are also being considered to explain these anomalies without resorting to the existence of a massive planet. These theories explore concepts such as the influence of a ring of trans-Neptunian objects or a massive disk of objects located in the outer reaches of the solar system. The first alternative theory to emerge is the existence of a dense ring of trans-Neptunian objects. Trans-Neptunian objects are icy bodies located beyond Neptune, mainly in the Kuiper Belt. The idea is that these trans-Neptunian objects, by aggregating in a kind of super ring, could explain the gravitational perturbations observed without the need to postulate a massive planet like Planet 9. In this hypothesis, this ring would be made up of numerous small objects, perhaps billions of trans-Neptunian objects spread over a vast area of the outer solar system. Together, the cumulative mass of these objects would be sufficient to create the gravitational effects measured by astronomers. Rather than a single giant planet, it is the distribution of these trans-Neptunian objects that would exert a gravitational influence on other celestial bodies. This theory is based on the idea that in certain remote regions of the solar system, the density of trans-Neptunian objects could be much higher than we have observed to date. This hypothesis has several advantages. Firstly, it avoids invoking an invisible massive planet, which would be particularly difficult to detect due to its great distance from the Sun. In addition, a dense ring of trans-Neptunian objects could explain the orbital clusters observed around certain regions of the outer solar system, notably those of Sedna and other extreme trans-Neptunian objects. These clusters could be the result of gravitational interactions between the objects themselves, rather than a force exerted by an as-yet undiscovered planet. Another hypothesis proposes the existence of a massive disk of trans-Neptunian objects located in the farthest reaches of the solar system. This disk would be made up of debris from the formation of the solar system, similar to the objects in the Kuiper Belt, but much further away. It would stand out from the other theories in terms of size and density. This disk would be more massive and more extensive than the simple ring proposed by the first hypothesis. In this theory, the massive disk of trans-Neptunian objects would exert a coherent but diffuse gravitational force on the entire outer solar system. Instead of a single planet exerting a localized, concentrated force, this disk would produce a global gravitational effect that would disrupt the orbits of objects beyond Neptune. The gravitational force of this disk, although spread over a large area, could influence the trajectories of trans-Neptunian objects, creating anomalies similar to those attributed to Planet 9. The massive disk hypothesis has the advantage of offering a distributed explanation for the extra gravity detected in the outer solar system. It eliminates the need to search for a single massive invisible planet, preferring instead the idea that many small objects acting collectively produce the observed effects. This hypothesis could also explain why we haven't yet detected Planet 9. There would simply be no Planet 9 to detect, but rather a vast array of smaller objects. While these alternative theories present some interesting ideas, they are not without their challenges. One of the main obstacles to the ring of trans-Neptunian objects or massive disk hypothesis is the total mass required to explain the gravitational anomalies. Current estimates of the mass of the Kuiper Belt and trans-Neptunian objects suggest that these regions contain far less matter than would be needed to generate the observed effects. In other words, even if these regions contain a large number of objects, their combined mass may not be sufficient to create the gravitational perturbations associated with the Planet 9 hypothesis. What's more, the distribution of objects in these theories raises questions. For these cumulative masses to explain the observed effects, trans-Neptunian objects would have to be distributed in a very specific way. This would imply that we only see a fraction of these objects, and that many of them are in unexplored regions of the solar system. This remains speculative, however, as our current observations of the Kuiper Belt and trans-Neptunian regions do not reveal a sufficiently dense distribution of objects to fully support these hypotheses. It's also possible that neither of these theories alone provides a complete explanation. Indeed, a combination of the two hypotheses, i.e. the existence of a dense ring of trans-Neptunian objects and a massive disk, could provide a more comprehensive solution. In this scenario, some of the gravitational perturbations could be due to the interaction between these objects distributed in a vast massive disk, while others could still be attributed to the presence of a distant planet. Proponents of the Planet 9 hypothesis do not necessarily reject the idea of a massive disk or a ring of trans-Neptunian objects. On the contrary, they consider that these elements could coexist with Planet 9, contributing to the complexity of gravitational interactions in the most distant regions of our solar system. As a result, two models for the evolution of Planet 9 have been proposed. In 2016, astrophysicist Esther Linder and Christoph Mordesini from the University of Bern developed a model to study the evolution of Planet 9. According to their simulations, this mysterious planet would have very distinct physical and thermal characteristics. First of all, the planet would have a diameter around 3.7 times that of the Earth. Despite this imposing size, it would be extremely cold, with an average temperature of around -226 degrees Celsius, or -375 degrees Fahrenheit. Although relatively dim in the visible spectrum, with an apparent magnitude between 20 and 22, it would shine much brighter in the infrared, where its apparent magnitude would reach 11. This means that in this wavelength, the planet would be around 10,000 times brighter, making it easier to detect with infrared-sensitive telescopes. In terms of composition, Planet 9 would resemble a small version of Neptune, with a well-defined layered structure. At the center would be a core composed mainly of iron, where the temperature would reach 3,400 degrees Celsius or 6,200 degrees Fahrenheit. Around this core, a mantle of silicates, including bridgmanite, the most abundant mineral on Earth, would form a solid layer. This would be followed by a second mantle, this time of water ice at temperatures of around 1,800 degrees Celsius, or 3,720 degrees Fahrenheit. Finally, according to the same model, the planet would be enveloped by a gaseous mantle, composed of hydrogen and helium, before ending with an atmosphere, also made up of these two elements, but much colder, with a temperature of just -226 degrees Celsius or -375 degrees Fahrenheit. This model therefore proposes that Planet 9 is a kind of mini Neptune, with a layered structure and atmosphere similar to those of gas giants, but smaller and more distant, which explains its icy temperature and infrared luminosity. These characteristics make the planet difficult to observe in the visible spectrum, but open up new prospects for detecting it using instruments capable of capturing infrared light. The second model is explained by astrophysicists Jacob Schultz and James Unwin, who have proposed a fascinating and intriguing theory. What if the mysterious Planet 9 was not a planet, but a primordial black hole? This hypothesis, though surprising, could explain why we haven't yet succeeded in detecting this object in the farthest reaches of our solar system. Indeed, a black hole neither emits nor reflects light, making it extremely difficult to detect using traditional astronomical observation methods. According to these scientists, Planet 9 could be a primordial black hole, a hypothesis seriously considered by many scientists. Unlike conventional black holes, which form following the collapse of massive stars, a primordial black hole is thought to have originated shortly after the Big Bang. This type of black hole, which is extremely dense and compact, would be tiny by astronomical standards, in this case the size of a tennis ball. Yet despite this small size, it would possess a mass large enough to disrupt the orbits of Trans-Neptunian objects, as has been observed. So how do you detect such a small black hole? Schultz and Unwin suggest that the traditional method, which relies on observing visible light, would not be effective in locating such a peculiar object. However, a primordial black hole, although dark, could be surrounded by an accretion disk, which represents a zone where matter gravitates around the black hole before being absorbed into it. This disk could emit X-rays or gamma rays, energetic signatures that could be detected by specific instruments. The idea that a black hole could have been captured by our solar system is a bold one. Scientists point out that the motion of trans-Neptunian objects, celestial bodies located beyond Neptune, could be influenced by a massive but invisible object, such as a primordial black hole. This hypothesis offers a plausible explanation for the gravitational anomalies that led to the search for Planet 9. In 2024, a new study proposed a different approach to exploring the existence of the mysterious Planet 9. Instead of focusing on trans-Neptunian objects with highly elliptical orbits, which are difficult to observe because they remain far from Neptune, researchers studied those that cross Neptune's orbit, known as Posido-cruiser objects. These objects are easier to observe and model. The idea behind the study was to compare the number of these objects in two scenarios, one where Planet 9 exists and one where it does not. In analyzing the results, the researchers found that there were too few NEOs observed to be explained without the presence of a massive planet such as Planet 9. This reinforces the hypothesis of the existence of such a planet in our solar system. Although the Planet 9 hypothesis has gained in popularity in recent years, not all astronomers and physicists are convinced of its existence. Many of them question the idea, putting forward arguments that highlight the uncertainties and limitations of this theory. The Planet 9 hypothesis is mainly based on the explanation of orbital anomalies observed in the outer reaches of the solar system, notably in the trajectories of trans-Neptunian objects. However, some astronomers and physicists suggest that these anomalies could be the result of as-yet undiscovered gravitational phenomena, rather than the presence of an invisible massive planet. This approach opens the door to fascinating alternatives that could challenge our current understanding of the solar system. One intriguing possibility is that the orbital anomalies of trans-Neptunian objects are influenced by gravitational forces outside the solar system. Our Sun is not isolated in space. It is part of a group of stars, and gravitational interactions with these neighboring stars could influence trans-Neptunian objects. Stars sometimes pass relatively close to the solar system, and even if these encounters are rare, they can have an impact on objects located at the edges of the solar system. These transits could cause perturbations in the orbits of certain trans-Neptunian objects, creating the anomalies observed, without the need for a massive planet to explain these phenomena. Other, more radical theories envisage a modification of the laws of gravity themselves. For example, some variants of the MOND, or Modified Newtonian Dynamics theory, propose that the laws of gravitation we know do not apply in the same way in areas of very weak gravitational forces, such as the outer reaches of the solar system. This could explain why the orbits of trans-Neptunian objects do not correspond exactly to the predictions of traditional physics, without the need to postulate the existence of an unknown planet. Some astronomers argue that the clustering observed in the orbits of trans-Neptunian objects could be due to observational bias. Indeed, trans-Neptunian objects are extremely difficult to detect, and current observations only cover a small portion of the sky. This means that the clusters observed may not be representative of the actual distribution of objects in the outer solar system. In other words, the apparent groupings could simply be the result of the way astronomers point their telescopes, rather than any real gravitational influence exerted by an unknown planet. The discovery of a new planet, like the supposed Planet 9, would have a major impact on our understanding of the solar system and the way we model it. Currently, the classical model of the solar system is based on the idea of 8 main planets, organized in a relatively simple way around the Sun, with a clear division between inner rocky planets and outer gas giants. If a new planet were confirmed, it would call into question several fundamental aspects of our vision of the solar system. Planet 9 would be located well beyond Neptune, at a much greater distance than the other known planets. Its far-flung eccentric orbit would considerably push back the boundaries of the solar system, altering our perception of its size and scope. While Neptune, the current last planet, lies around 4.5 billion kilometers from the Sun, Planet 9 could orbit more than 100 billion kilometers away. This would redefine the boundary of the solar system and expand our understanding of its external structure. Such a discovery would also force us to revise our classification of Trans-Neptunian objects and objects in the Kuiper Belt, as the gravity of this new planet could explain certain orbital anomalies observed in this region. The discovery of such a distant planet would also lead us to reassess the role of giant planets in the formation and dynamics of the outer solar system. One of the main implications of the discovery of Planet 9 would be to revise current theories on planet formation. The presence of a massive planet so far from the Sun could indicate that planetary formation processes are more complex than we thought. Traditionally, giant planets form closer to the central star before migrating outwards, but Planet 9 could potentially have been ejected at an extreme distance due to an interaction with Jupiter or Saturn. This discovery would call into question models of planetary migration, and could imply that other star systems could also host as yet undiscovered distant planets. This would pave the way for new hypotheses on the formation of planetary systems in the universe, and on the frequency of this type of isolated planet. Such a major discovery would also have a significant impact on astronomical research. Scientists would focus more on exploring distant regions of the solar system, which have hitherto been neglected due to their distance and the difficulty of observing them. This could lead to the creation of new technologies to better observe these remote regions, and the organization of ambitious space missions such as sending probes to study this new planet. In 2020, a new theory was proposed by researchers at Harvard University, suggesting not only that the famous Planet 9 might exist, but that it might have been influenced by a stellar companion that our Sun once had. Scientists have hypothesized that the Sun was once part of a binary system, meaning it would have had a twin in its original cluster. This long-lost companion could explain the formation of the Oort cloud, an immense hypothetical region of icy debris that surrounds our solar system. This cloud is often seen as the origin of long-period comets. The Oort cloud is thought to lie at incredibly distant distances from the Sun, ranging from 2,000 to 100,000 astronomical units, whereas the orbit of Pluto, for example, lies between 30 and 50 astronomical units. According to this theory, the Sun's stellar companion would have helped capture some of this debris to form this giant cloud. Scientists explained that binary systems like the one proposed for our Sun are far more effective at capturing space objects than stars alone. Indeed, according to this hypothesis, this missing companion would have enabled the capture of many distant objects and could also explain the formation of Planet 9. This theory would improve on existing models which struggle to explain certain features of the Oort cloud and Trans-Neptunian objects such as Planet 9. If the Sun had indeed had a stellar companion, this would considerably increase the chances of having captured an object the size of Planet 9. Scientists estimate that the chances of capture would have been multiplied by 20 if 2 stars had been present. Later, a nearby star would have disrupted this system, leaving our Sun alone. Currently, researchers Brown and Batygin are using the Japanese Subaru telescope located in Hawaii, which has a better chance of spotting it than other telescopes such as Pan stars. If this search fails, they will turn to the future Vera C. Rubin Observatory, currently under construction in Chile. This ground-based telescope, equipped with the world's largest digital camera, will explore the solar system in greater depth than ever before, much as the James Webb Space Telescope has done for the observable universe. The observatory is scheduled to open in late 2025. With this state-of-the-art telescope, it's possible that Planet 9 will be discovered within 2 years, according to Brown, although he admits to having made this prediction every year since 2016. Other astronomers share this optimism, believing that the discovery could be made within a year of the Rubin Observatory becoming operational. But if the telescope fails to locate the planet within the first few years, scientists explain that the Planet 9 hypothesis will be all but abandoned. The journey into the depths of space in search of Planet 9, whether or not it leads to a discovery, underlines the power of human curiosity and our insatiable quest for knowledge. We are approaching the nearest star system to our Sun. This is Proxima Centauri, a stellar and planetary system that also goes by the name of Alpha Centauri c. You'll understand why it's called Alpha Centauri in a moment. We are in the constellation of Centauri, only 4.2 light-years from Earth, and therefore still in our beautiful and luminous Milky Way. The luminous object you have before you is a red dwarf. These are very common in our galaxy. They represent nearly 80% of the stars in the Milky Way. The apparent magnitude of Proxima Centauri, which is equal to 11.05, does not place it in the category of the brightest stars, the most radiant stars being of first magnitude. In fact, 85% of the energy it emits is not visible to our eyes, being mainly in the infrared wavelengths. To the naked eye, its luminosity in visible light is almost 650 times less than that of our Sun. Proxima Centauri is therefore of spectral type M5, which explains why it was only discovered in 1915. With an actual diameter of 200,000 kilometers or 125,000 miles, it is 7 times smaller than the Sun, which is 1.5 times the size of Jupiter, the largest planet in our solar system. Its mass is about 12.3% of the Sun's. But Proxima Centauri has a medium density, and its density is much higher than that of the Sun. Unlike our star, which transmits its energy to the outside by radiation, Proxima Centauri transmits it by physical movements of the plasma. The interior of this star is therefore entirely convective. The helium which is produced by nuclear fusion, instead of accumulating in the center of the star, circulates inside it. This results in a convection phenomenon which generates a permanent magnetic field. This magnetic energy is extracted from the object in the form of stellar eruptions comparable to solar flares. Some of these explosions can reach incredible dimensions, corresponding to the size of the star itself, which considerably increases its total luminosity during a certain period of time. Nearly 80% of the star's surface is active, which is far beyond the activity that we know of the Sun. This is why the temperature of its corona, even outside its peaks of activity, remains higher than that of the Sun. It reaches 3.5 million degrees Celsius, or 6.3 million degrees Fahrenheit, while our Sun does not exceed 2 million degrees Celsius or 3.6 million degrees Fahrenheit. This violent activity is nevertheless less important than many other red dwarfs can undergo, probably because of the advanced age of this star, which is estimated at several billion years. Proxima Centauri is a planetary system. The star does not evolve alone, far from it. It is accompanied by not one, but 3 planets orbiting it. The first, Proxima Centauri b, is a telluric planet located in the habitable zone of its host at a distance of 7 million kilometers. Its orbital period is just over 11 Earth days. Its mass, about 1.3 times that of our Earth, and its equilibrium temperature suggest that there could be water in a liquid state on its surface. But if we assume that this exoplanet has no atmosphere, which has been destroyed by repeated stellar eruptions, no form of life could be found there. The proximity of the 2 objects probably leads to a synchronous rotation, which means that this planet permanently shows the same face to its star. As a result, Proxima Centauri b could experience very high temperatures on its exposed side, hindering the presence of liquid water, while its hidden side would be extremely cold, covered mostly by ice. But what about the regions located between these 2 zones? Do you believe, in case of the presence of an atmosphere, that a life is possible at the level of the Terminator, this border connecting the 2 faces? The second planet that orbits Proxima Centauri is a cold super-Earth of the mini-Neptune type. This is Proxima Centauri c. With a mass of 5.8 times that of the Earth, it is located at about 1.5 astronomical units from its star. Its orbital period is 1900 days, or a little more than 5 Earth years. Finally, an exoplanet, whose mass is a quarter of that of the Earth, was detached in 2022. It is Proxima Centauri d, an exoplanet distant from its host by only 4 million kilometers or 2.5 million miles. Life on this planet, which orbits in only 5 days, is fatally impossible because of its proximity to the star. Furthermore, Proxima Centauri, although discovered late, was found to belong to an even larger system. In fact, it is only the 3rd and smallest star in a triple system, Alpha Centauri, which has been known for much longer. Do you see, not far from there, these 2 stars which make you eye? I suggest that we get closer to these 2 bright stars, Alpha Centauri A and Alpha Centauri b, which form the main duo in this triple system. They are distant from their 3rd companion by nearly 13,000 astronomical units, or 1,950 billion kilometers, or 1,200 billion miles. This distance, which is only 5% of the distance between Alpha Centauri AB and our Sun, still suggests an orbital period of Proxima Centauri between 507,000 and 613,000 years around the main duo. The distance and its low orbital velocity explain why Proxima Centauri has long been excluded from this system, to which it is nevertheless gravitationally bound. To the naked eye, this binary system, because of the proximity of its components, appears from our Earth as the brightest star in the constellation Centauri, and the 3rd brightest in our sky, with Sirius and Canopus surpassing it. Similar to the Sun, the 2 stars that compose it are respectively of class G2 and K1. Alpha Centauri A, also named Rigil Cantaris, is the largest of the stellar duo, with a mass equivalent to 1.1 solar masses and a luminosity 1.519 times that of the Sun. It is a yellow dwarf that is 10% more massive than the Sun, with a radius 22% larger. In short, you are looking at the twin sister of our Sun. Alpha Centauri B, also called Ptolemy, is slightly smaller and cooler than its companion. The mass of this secondary star is 90% of that of the Sun, and its diameter only 14%. Its luminosity is barely 45% of that of the Sun. Therefore, it has a main sequence of spectral type K, which gives it this more orange color. These two stars orbit each other in 80 years. Their orbits, slightly eccentric, bring them closer to each other by 11.2 astronomical units, or about 1.68 billion kilometers, which is the distance between the Sun and Saturn. When they move away, they can be up to 35.6 astronomical units, or 5.33 billion kilometers, or 3.1 billion miles, which is equivalent to the distance between Pluto and our Sun. Astronomy enthusiasts will have to wait until May 2035 to benefit from the next pericenter in order to observe this pair in optimal conditions. Their orbital period will then have brought them closer. But our interstellar journey gives you today the possibility to observe them as never before. So let's take advantage of it to know a little more. Do you think that this star system, which is home to stars resembling our Sun, could harbor any form of life? And why wouldn't there be, in this not-so-distant land, some hot and rocky planets with a lot of water, comparable to our Earth? If you look at the near environment of Alpha Centauri A, at first sight, no planet is visible. However, a candidate exoplanet named Candidate 1 has been studied by astronomers since 2021. Distant of about 1.1 astronomical units from the star, with a revolution estimated at 1 year, it could in fact be only a dust disk, or even an artifact. On the other hand, Alpha Centauri B could have several companions, even if they have not been confirmed by the scientific community. The first, detected in 2012, would be a planet whose mass, greater than 1.1 and 2.7 times that of the Earth, qualifies it as a super-Earth. It is called Alpha Centauri BB, or Gliese 559BB. Only this candidate orbits in a non-habitable zone with respect to its host star, on a short period of 3.24 days. Distant from 0.04 astronomical units, or only 6 million kilometers, or 3.7 million miles from its star, you can imagine that no life can develop there. The very high temperatures of this planet would be able to melt lead, but recent studies have shown that Alpha Centauri BB is actually a statistical ghost. It has therefore disappeared from the list of exoplanets. The second companion, Alpha Centauri BC, is another candidate planet that seems to evolve little further than the previous one, with an orbital period of less than 20 days. Its size, 92% that of the Earth, would have made it an ideal telluric planet. But once again, its proximity to the star that hosts it makes the presence of water in a liquid state on its surface impossible. At present, it is finally near the smallest star of this triple system, Proxima Centauri, that we are most likely to discover a habitable planet, at least in part. But let's see what the next solar systems can tell us. Although more distant, they could hold some nice surprises. Let's start with Barnard's Star, which is located a little further away in the constellation of Ophiuchus, 5.9 light-years from our Sun. Despite its proximity to our solar system, its low luminosity prevents its observation without a telescope. Indeed, it is a red dwarf of spectral type M4. In other words, it is an old lady. Of an advanced age of some 10 billion years, it presents a deficiency in metal. It contains barely 25% of the amount contained by the Sun. Moreover, it has lost a lot of its rotation energy. This one is 130 days, which is relatively slow compared to the one of the Sun, which makes it in 25 days only. Much less radiant than our Sun, it is hardly more luminous than 100 full moons cumulated. Its mass represents 17% of solar mass, and its radius 15 to 20% of the Sun's. However, this star monopolizes the sphere of scientists for various reasons. Under its calm airs, it can still show strong fits of anger, resulting in significant stellar activity. Moreover, in 1998, an intense stellar flare was observed. The temperature reached during this eruption exceeded 7,700 degrees Celsius, or 13,800 degrees Fahrenheit, more than double the temperature of the star. Barnard's Star is therefore a so-called eruptive star. In addition, it is sometimes called the runaway star of Barnard. If the stars appear as fixed points in our night sky, they all move in our universe. But these movements, when compared to the scale of our human lifetimes, seem insignificant. However, Barnard's Star holds a speed record. It is the fastest moving star in our Earth's sky, not following the general flow of stars around our Milky Way. To give you an idea, this star moves across our sky about one full moon width over a period of 174 years. This may seem extremely slow to you, but compared to other stars, Barnard's Star feels like it is spinning through the sky, with a relative lateral speed, that is, sideways to our Sun, of 90 kilometers per second, or 55 miles per second. Its radial velocity brings it closer to our solar system at the crazy speed of 140 kilometers per second, or 85 miles per second. By the year 11,800 AD, Barnard's Star should be only 3.8 light-years away from our Earth. You are probably wondering why we are visiting Barnard's Star. Why are we interested in this isolated star that doesn't seem to belong to a system? In fact, Barnard's Star is a small planetary system. This star, which has monopolized planet hunters for several decades, has been the subject of more than 770 observations. Astronomers saw their efforts rewarded in 2018. An exoplanet does orbit near Barnard's Star. It is Barnard's Star B, also known as the planet Barnard B. This rocky planet has a mass equivalent to 3.2 times that of Earth, making it a super-Earth. Distant from about 60 million kilometers or 37 million miles, twice as close to its host as the Earth is to the Sun, it revolves in 233 days. But this close distance is not enough to place it in the habitable zone of this red dwarf. The exoplanet Barnard B, compared to our Earth, receives only 2% of the energy of its star. It evolves just beyond what is called the ice line. Its surface temperature is so cold, approximately minus 170 degrees Celsius, or minus 274 degrees Fahrenheit, that the presence of liquid water is highly unlikely. This planet cannot support any form of life. Too bad. This discovery, which is the result of an important collaboration between many scientists from all over the world, follows 20 years of studies performed with 7 different instruments. However, other candidate planets are being studied in this stellar region, including Barnard Star C and Barnard Star D. But so far no study has been able to confirm their presence. Astronomers now know that they are likely to discover many other planets of this type near red dwarfs, especially as technologies continue to progress. The only thing left to do now is to find an exoplanet that has the right conditions to support life. Let's continue our interstellar journey and reach the binary system Lumen 16, which is only 6.5 light-years away from our Sun. Composed of 2 brown dwarfs, it is located in the southern constellation of the Sails. To date, it is the closest known pair of brown dwarfs to our solar system. Their recent discovery, which dates back only to 2013, was the result of a 13-month mission by NASA's WISE spacecraft. It acquired about 1.8 million images of asteroids, stars, and galaxies. But first, what is a brown dwarf? In reality, it is an object too massive to be considered a gas giant, but not massive enough to be a star, being unable to trigger nuclear fusion at its center. Brown dwarfs are sometimes compared to failed stars. The main component of this binary system is of spectral type L8. The second, even less bright, is also a late bloomer that appears closer to the transition threshold. These 2 objects, which are separated by more than 3 astronomical units, orbit each other in about 25 years. This slowness is explained by their low mass, although it represents about 30 times that of Jupiter. Like Jupiter, the 2 brown dwarfs are subject to strong winds, as evidenced by the bright stripes running parallel to their respective equators. If you take a closer look at Object B, you will see a complex structure of irregular clouds on its surface, sometimes light, sometimes dark. Composed of iron droplets and other minerals, these disparate clouds present extreme weather conditions, with temperatures exceeding 1,000 degrees Celsius or 1,832 degrees Fahrenheit. But let's be careful and keep our distance from this molten iron rain. Because of their low luminosity, these 2 red dwarfs offer scientists an open-air laboratory that should allow them to study this type of object more easily. Brown dwarfs could reveal the secrets that govern planetary evolution, but also the formation of stars. They could even allow the discovery of exoplanets. While brown dwarfs are not massive enough to allow hydrogen fusion like stars do, they do cool slowly as they contract, and their surface gravity increases. As a result, the surface temperature of a brown dwarf can vary considerably. It can reach degrees almost comparable to those of a star, and on the contrary, degrees as low as those of a cold planet. Their age and their physical composition are as many parameters that make them different from each other. They can then present great diversity of colors and spectral characteristics. Slight perturbations are observable in the orbits of these two brown dwarfs. A planet is probably at the origin of these variations. But to find this unconfirmed object, we must know on which side to look, and at what distance. Because as we have already seen, even at very large distances from each other, objects can be linked. Let's go now to the constellation of Hydra to discover the star Y0855-0714. This star is 7.2 light-years away from our Sun. This short distance on the cosmic scale makes it the fourth closest star to our Sun. Its physical characteristics place it in the category of sub-brown dwarfs, or brown dwarfs of planetary mass. Its mass corresponding to 1% of the solar mass. Its formation, identical to that of stars or brown dwarfs, is the result of the collapse of a gas cloud. Only its mass, which is 10 masses of Jupiter, remains lower than the 13 masses allowing it to generate the thermonuclear fusion of deuterium, so that it can claim the status of star. If this type of object is often classified in the category of brown dwarfs of planetary mass, some scientists consider them as planets floating freely in the cosmos. Y0855-0714 is even cataloged by some as a rogue planet, especially since it seems to evolve alone, without any companion at its side. Its discovery, made possible by WISE, NASA's Wide Field Infrared Explorer, dates back to 2014. This star, whose radius is slightly smaller than Jupiter's, has average temperatures worthy of the North Pole, from about -48 degrees Celsius to -13 degrees Celsius, or between -54 degrees Fahrenheit and 9 degrees Fahrenheit. Colder than Earth's average temperatures, but warmer than those on the surface of Jupiter. Therefore, among all its fellows in interstellar space, it is the coldest object of all. But this is not what surprised astronomers the most when they observed it. Let's get a little closer to this failing star. Its spectral type Y allows us to observe its surface more closely, without the need to protect our eyes. We can admire in an atmosphere tinted with azure shades, clouds similar to those surrounding our beautiful blue planet. Isn't it extraordinary? These clouds are composed of water ice crystals and sodium sulfide. This is a first for scientists. If water vapor has already been detected in the atmospheres of exoplanets, this is the first time that water clouds are observed outside our solar system. Even at the closest to our planet, these observations are generally only possible on Earth or Mars. The giant planets are so cold that the ammonia ice clouds mask the water clouds, as on Jupiter and Saturn, and the atmospheres of Neptune and Uranus prevent any visibility. All in all, this so-called failing star is of great interest to the scientific community, especially since it evolves alone in interstellar space. As you have probably noticed, no other object seems to be gravitationally linked to this failed star. Observations looking at it therefore cannot be subject to interference from a nearby star that could cause any glare. Let's now turn our attention to another star system, also located a short distance from our solar system. Let's go to the constellation Leo, where a red dwarf has, like our Sun, a corona. Here we are approaching Wolf 359, a star that is certainly quite pale, with a spectral type of class M6.5, but which hosts two exoplanets. They are respectively named Wolf 359b and Wolf 359c. Wolf 359 is one of the smallest stars known to date, its mass of 0.09 solar masses being at the lower limit. Indeed, a star whose mass is lower than 0.08 solar mass is not massive enough to ignite the hydrogen of its core. Wolf 359 is then at the limit to be considered also as a brown dwarf. Because of its small size, its radius being only 0.16 solar radius, it is entirely convective. The helium produced in its center arrives at its surface thanks to the movement of the plasma. Because of this weak and slow production of energy, it will probably remain in this state much longer than our Sun, which burns its cartridges at high speed. The life of the latter is estimated at 10 billion years, and we know that it has reached 4.55 billion years. In place of our Sun, the faintness of Wolf 359 would represent about 10 times the brightness of our full moon. Not enough to cause us the slightest sunburn, even worse, not enough to hope for any presence of life on our planet, which would then be covered with ice. However, this young spinner, at least 100 million years old, and whose projected rotation speed is less than 3 kilometers per second, or 2 miles per second, is a flare star. In other words, a variable star. Of UV Ceti type, it undergoes sometimes brutal increases of its luminosity on all its spectrum. Its magnetic activity induces brief eruptions which can occur at a rate of 32 events over a period of 2 hours, most of them being microeruptions. Its surface temperature, much lower than that of our Sun, is nevertheless 2,500 degrees Celsius, or 4,532 degrees Fahrenheit. This temperature is low enough for the chemical compounds to remain long enough to be observed with their spectral lines. In 2001, molecular lines composed of carbon monoxide, iron hydride, chromium hydride, water, magnesium hydride, vanadium oxide, or titanium oxide could be observed for the first time from a terrestrial telescope. Apart from the Sun, Wolf 359 is therefore the first star to expose the spectrum of its corona to the light. The study of its spectrum revealed the absence of lithium lines. This element has probably been entirely consumed by fusion in the core. This is the parameter that allows us to conclude that this star must be at least 100 million years old. As we have seen, Wolf 359 is not alone. It has 2 companions. 2 planets orbit around it. The first, Wolf 359b, is 276 million kilometers, or 170 million miles away, and the second, Wolf 359c, is close to 2.7 million kilometers, or 1.7 million miles. The more distant of the two has a mass of about 43.9 Earth masses and orbits Wolf 359 over a period of 2,938 days. The closer one, Wolf 359c, is much less massive, with its 3.8 Earth masses. It orbits its star in 2.7 days. Unfortunately, these 2 planets are either too far away or too close to their host to be located in the habitable zone, which extends from 3.6 and 7.7 million kilometers away, or between 2.2 and 4.7 million miles. Wolf 359b would be so cold that it could only be covered by a thick coat of ice, while its companion, Wolf 359c, would suffer from temperatures too high for water to remain in liquid state on its surface. Our efforts to find a potentially habitable exoplanet will therefore have to focus on another star system. Another red dwarf, located in the Big Dipper constellation and 8.3 light-years away from our Sun, is particularly promising. Let's join the second Argelander star, better known as Gliese 411, or Lalande 21185, an old lady between 5 and 10 billion years old. This red dwarf of type MV5 is cold and dark. Its luminosity, which is 6,000 times lower than that of our Sun, does not prevent it, however, from being among the brightest red dwarfs in the solar neighborhood. Its apparent magnitude is only 7.47, so it cannot be observed with the naked eye. It has all the characteristics of a half-sun, a mass of about 46% of solar mass, and a diameter equivalent to 40% of that of the Sun. If its mass had reached 50% of solar mass, it would probably have entered the category of red giants. Its surface temperature, which is about 3,328 degrees Celsius, or 6,022 degrees Fahrenheit, or 62% of that of the Sun, can undergo sudden variations as well as its luminosity. Indeed, Gliese 411 is a so-called eruptive star, a flare. The eruptions on its surface are as unpredictable as they are spectacular, especially since the excess luminosity produced contrasts with the usual pallor of the star. At first sight, apart from its spectral anger, this star has nothing extraordinary. However, it integrates the list of interesting objects for exoplanet hunters. On the one hand, because of its proximity to our Earth, and on the other hand, because of its constant radial velocity. It is a perfect example of the stability level of red dwarfs, although it moves perpendicular to the galactic plane at high speed with an average of 47 kilometers per second, or 30 miles per second. In its interstellar course, Gliese 411 undergoes, however, astrometric perturbations. The study of these variations has established that this red dwarf is indeed part of a multiple system. Since 1996, it is known that not one, but two, or even potentially three planets are in orbit around Gliese 411, which is therefore the fourth closest planetary system to our Sun, after Alpha Centauri, Barnard's Star, and Wolf 359. The first planet is called Gliese 411b. It is a super-Earth. Its mass corresponds to 3 Earth masses. Very close to its star, at 0.08 times the distance Earth to Sun, it completes its orbital period, which is very circular, in only 13 days. Gliese 411b is 5 times closer to its host than Mercury is to the Sun, and although this star is less hot than the Sun, the planet is not in the habitable zone. It receives 3.5 times more energy than the Earth receives from the Sun, and must therefore have strong similarities with Venus. A second planet evolves at a little less than 3 astronomical units from the mother star. This is Gliese 411c. This exoplanet, whose mass exceeds 13 terrestrial masses, covers its orbit in 2,946 days. It is therefore a Neptune-like planet, located well beyond the habitable zone. Finally, a third planet could also interfere with the main star, placing it in the category of quadruple systems. Named Gliese 411d, it is 0.5 astronomical units away from its host. With a mass equivalent to 4 Earth masses, it has an orbital period of 215 days. It remains to be seen if its temperature and atmosphere are suitable or not for any form of life. What about you? What do you think about it? But let's leave this question aside for the moment. A star, sparkling like no other, attracts your attention, and for good reason. You are looking at Sirius, the brightest star after the Sun in our winter sky. You know, the one that flashes in the sky, reminding you of the intermittent lights of a plane at high altitude. Moreover, its name, which was not chosen at random, means bright in Greek. We find traces of its sparkling presence since the dawn of time. For the ancient Egyptians, the Nile star, as they called it, announced the periods of flooding of the river. In Chinese astronomy, it was called the celestial wolf, while the Greeks associated it with the dog of Orion, then called Sirius. This star also played a fundamental role for Polynesian navigators by serving as a landmark. The stars were their only reliable tool for orientation at sea, and Sirius, easily recognizable, marked the zenith of the most honored place of worship in the entire Polynesian region. It is located in the constellation of the Great Dog at a distance of 8.6 light-years from our own system. That is why it is also known as Alpha Canis Majoris, being the brightest star in this constellation. Its apparent magnitude is -1.46. To be clear, this negative number means that Sirius is brighter than our Sun, a magnitude of 1 being equivalent to the solar luminosity. This is why, despite a distant, but at the same time so close to our solar system on the scale of the cosmos, Sirius, which is classified in the category of white stars, appears so bright. Its brightness is punctuated by variation when observed from Earth. As you can see, however, it does not blink any more than our Sun. This effect is due to the fact that Sirius is located very low on our Earth's horizon. The light emitted by the star must therefore cross a large part of the atmosphere before reaching us. It is therefore more or less masked by the turbulence of the environment that separates us from it, hence its flickering. During our approach, if you look carefully at Sirius, you see that it is in fact a binary star. It is composed of 2 stars. The main one, Sirius A, is a white, slightly bluish star of spectral type A0 or A1. More luminous than our own star, it is 2.3 times more massive and 1.8 times larger than our Sun. I let you imagine the heat that reigns on its surface, its temperature being higher than 9,600 degrees Celsius, or 17,300 degrees Fahrenheit. That is to say, much more than our Sun, which burns at 5,504 degrees Celsius, or 9,930 degrees Fahrenheit. All these characteristics evoke the relatively young age of Sirius, which should not have more than 200, even 250 million years. It has for companion a white dwarf named Sirius B. The latter, because of its small size, its proximity to Sirius A, and its low magnitude of only 8, was discovered only very late in 1862. As a white dwarf, Sirius B has a size comparable to that of the Earth, while its mass is equivalent to that of the Sun, and its estimated temperatures are 3 times higher than those of Sirius A. Separated from the main star by an average of 19.5 astronomical units, or 19.5 times the distance between the Earth and the Sun, it orbits around it over a period of 50 years. Because of a strongly marked elliptical orbit, the distance between these two stars can vary from 8.1 to 31.5 astronomical units. This maximum distance will soon be reached by 2024 to 2025, while the next passage at the periastron of the system, i.e. the moment when the two stars will be the closest, is planned for 2044. This binary system is waving alone in the cosmos. No planet has yet been seen in its vicinity. Sirius being a young star, it is unlikely that exoplanets are in orbit around it. However, since 2018, NASA has been exploring this bright object with the Transiting Exoplanet Survey satellite. And who knows, its high brightness could mask one or even several planetary objects. At almost the same distance from our Sun, another stellar duo awaits us. Let's join, at 8.7 light-years from our solar system, Luyten 726-8, a binary system hosting two stars, BL Ceti and UV Ceti. They are once again two M-type red dwarfs, probably younger than our solar system. With a low luminosity, they are not visible to the naked eye. This is why they were only discovered in 1948. These two stars, like twin sisters, have many similarities. Both have almost identical masses, radii, and luminosities. Their mass is 10% of the solar mass, their radius 14%, and their combined luminosity is 11,000 times less than that of the Sun. It is therefore not surprising that we detect an identical temperature on the surface of these two stars, which is close to 2,330 degrees Celsius, or 4,220 degrees Fahrenheit. If the two stars orbit around a common barycenter over a period of 26.5 years, their orbits are marked by a strong eccentricity. The distance between them can therefore vary between 2.1 and 8.8 astronomical units, causing strong tidal forces between the two objects. BL Ceti, the main component of this duo, has a luminosity 6,000 times lower than the Sun, while the secondary star, UV Ceti, has a luminosity 4,000 times lower. UV Ceti is the better known of the two. The latter rotates very fast, with a rotation of only 0.2 days. Its rotation speed feeds a powerful magnetic field, where bubbles, charged with matter by the convection currents typical of red dwarfs, trigger important eruptions. UV Ceti is therefore a flaming star. During one of its numerous eruptions, its luminosity can be multiplied by 100 in a few seconds. At the same time, massive emissions of UV and X-rays ignite the star's environment. In 1952, the observation of UV Ceti allowed to count not less than 75 variations of its luminosity in only 20 seconds. This particularity places it in the category of variable stars, where, moreover, it serves as a reference. Indeed, other eruptive stars are sometimes included in the category of UV Ceti variables. The main star is less active. This is probably related to the fact that it has a lower rotation speed. Nevertheless, the motions of these two stars are at the origin of unusual stellar winds. Their surfaces are subjected to winds more violent than those experienced by the Sun, although weaker at equivalent distances. The resulting heliosphere extends to 10 or 20 astronomical units. During massive eruptions, this heliosphere can be expelled up to 100 astronomical units. When the eruption of one of the two stars is directed towards the second, a shock zone is created, somewhere between the two stars, giving a complex and non-spherical shape to the heliosphere surrounding UV Ceti. In short, the environment near this star system does not seem to be the most favorable to host a planet in the best conditions. This one, in addition to being subjected to stellar winds, would inexorably undergo the unpredictable explosions of anger of UV Ceti. However, oscillations have been noticed in the orbits of the two stars, in particular that of BL Ceti. But what could a planet located in this tiny part of space look like? A hypothetical planet orbiting UV Ceti would have no atmosphere, as it would be deteriorated in a few millennia by repeated flares. On the other hand, a planet orbiting BL Ceti could keep its atmosphere for more than 100,000 years. However, the important forces of tide undergone would dress this planet of a multitude of volcanoes, where the only existing rivers would welcome only the flows of a burning lava. Moreover, the strong fluctuations of temperatures would have reason of the rock present on its surface, transforming it gradually into dust, which would mix with the volcanic ashes. A planet in orbit around these two stars would be more than 30 astronomical units away. Of course, it could contain its atmosphere, but its temperatures below minus 230 degrees Celsius or minus 382 degrees Fahrenheit would not be very attractive, and the luminosity on this planet would be null, except during strong stellar eruptions. In short, if the binary system Luyten 726-8 can be attractive by its spectacular side, it is not very welcoming. Ross 154 is the 9th closest star system to our Sun. Located in the constellation of Sagittarius, it is 9.7 light-years away. Composed of a main sequence star of spectral class M3.5V, it is not visible to the naked eye from our Earth. Ross 154 is therefore, by definition, a red dwarf star, cold and dark. Its discovery by Frank Elmore Ross dates back to 1925. Ross 154, also named Gliese 729, has a mass equivalent to 17% of solar mass. Its size is about 20% of the Sun. Its apparent magnitude is only 10.44. The luminosity of this star is relatively low and represents only 0.4% of the Sun. Ross 154 is so small that it is not able to expel heat from the core at its surface, as do the larger red dwarfs. So it carries this heat to its surface by convection. Moreover, as you can imagine, the heat at its surface is much lower than that of our Sun. It is estimated at 3,019 degrees Celsius, or 5,460 degrees Fahrenheit. However, this star is not so ordinary. Like many red dwarfs, it is an eruptive star. Moreover, it integrates the category of UV Ceti-type variables. This flare star, during prodigious eruptions, can thus generate X-ray emissions comparable to, or even superior to, those of the Sun. In addition, to integrate the catalog of eruptive stars, Ross 154 is also part of the variable stars of type BY Draconis because of its variations of 0.03 magnitude, noted on a period of 2.87 days. In addition, its relatively low metallicity, estimated at 56% of that of the Sun, as well as its moderately high rotation speed of 3.5 kilometers per second, or 4 miles per second, allow to conclude that it is a relatively young star. Ross 154 is less than 1 billion years old. No planet has been detected in its environment. In any case, as for a large part of red dwarf stars, the numerous and violent eruptions which burst out at its surface would fatally harm any form of life which could develop in its habitable zone, the planet having necessarily to be close to the star. In the constellation of Andromeda, another red dwarf has almost the same characteristics. It is Ross 248, also known as Gliese 905. Located at 10.3 light-years from our solar system, it is similarly a flaming star that sometimes increases its brightness suddenly. Its mass is about 12% of the solar mass, its diameter is 7%, and its luminosity is 11,000 times lower than the Sun's. Periods of variability have been reported, ranging from 4.2 years to 120 days, and 5 others between 60 and 291 days. What if these were astrometric disturbances that could be attributed to the presence of an invisible companion? For the moment, no planet or other object has been found orbiting this star. In any case, the meteorological vagaries of this star can only harm any form of life in its proximal periphery, if it could have developed at all, especially since its reddish color would prevent any form of terrestrial-type plant life from properly carrying out its photosynthesis process. Another star system is of great interest to the scientific community. It is an orange dwarf star that plays hide-and-seek. Let's go to discover this mysterious star in the constellation of Eridanus, 10.5 light-years from our solar system. This is Epsilon Eridani, also known as RAN. Its apparent magnitude of 3.73 makes it the third closest individual star system visible to the naked eye. Younger than our Sun, it is between 200 and 800 million years old. Being a main sequence star of spectral class K2, the energy generated in its entrails by the nuclear fusion of hydrogen is diffused at its surface, where the temperature is higher than 4,800 degrees Celsius, or 8,670 degrees Fahrenheit. This is what gives it its beautiful orange color. Slightly smaller than our Sun, its mass is 82% of the solar mass, and its radius is 74% of the Sun's. Its average period of rotation is 11.2 days. Epsilon Eridani is thus more than twice less fast than the Sun. If its luminosity is only equivalent to 34% of the Sun's, on the other hand, it generates a level of magnetic activity higher than that of the Sun. The chromosphere and the corona that surround it are therefore much more dynamic. As a proof, the average intensity of the magnetic field at its surface is 40 times higher than that of the Sun, and its stellar winds 30 times more violent. But this activity is not regular at its surface. Some regions are much more active than others. Epsilon Eridani is therefore considered as a variable BY Draconis. It is a star that has a disconcerting behavior. Sometimes it brightens, sometimes it darkens. It has cycles of 27 years during which its brightness decreases considerably over a period of about 2 years. This decrease in intensity was last seen from 2009 to 2011. What gigantic object could shadow this star so much? It is known that Epsilon is surrounded by not one, but 2 rocky asteroid belts. One, 3 astronomical units away from the star, the second, 20 astronomical units away. However, they cannot explain this particularity. In fact, Epsilon is a binary star with eclipses. This means that it is accompanied by a dark object, probably a star, or even a pair of stars, surrounded by a disk of dust, dense and thick enough to make it invisible. These 2 stars are probably 30 astronomical units apart, and the diameter of the rings surrounding this pseudo-dark star must reach 20 astronomical units, occulting the main component like a curtain. However, Epsilon still reserves us a surprise. In addition to these variations of light, a study over 20 years of its radial speed has highlighted periodic variations. This observation has allowed to highlight the presence of a giant planet of the size of Jupiter in orbit around the star. This planet, named Epsilon Eridani b, or AE-Jur, follows a slightly eccentric elliptical orbit. Its semi-major axis is equivalent to the distance between our Sun and the asteroid belt. The size of this gas giant is estimated between 80 and 160% of the size of Jupiter. It completes its orbit in 7 years. If a planet could have formed in this environment, it is probably not alone, especially since the observed dust cloud has an asymmetry that could be explained by the presence of a second planet. This one would then be located much further away than the first one and would have a much longer orbital period. I now propose you to join another red dwarf. Yes, another one. Remember, red dwarfs alone account for about 80 to 85% of the stellar population in our galaxy. But this star should be of great interest to you, as it is considered by the scientific community as the best star to search for potentially habitable exoplanets. Let's discover Gliese 887, also known as Lacaille 9352. It takes the 12th place in the list of stellar systems closest to the Sun. Located in the constellation of Southern Pisces, 10.7 light-years from our Earth, it appears to be the brightest red dwarf in our sky and requires only a small telescope to be observed. Its luminosity is about 1% of that of the Sun. It is also the most massive of all red dwarfs, with nearly half a solar mass, at a distance of 6 parsecs from the Sun, or a little less than 20 light-years. But what makes this star even more exceptional is its low photometric variability, which makes it a quiet red dwarf like no other. Unlike its companions, Gliese 887 is less magnetically active and does not seem to ignite by triggering huge explosions or stellar eruptions. In other words, if there are planets orbiting in its narrow habitable zone, we could well detect traces of life there, and even, why not, consider terraforming them when technology allows it. This is very good news. On the one hand, the inactivity of this star greatly facilitates the remote observation of any exoplanetary atmosphere. On the other hand, exoplanets orbiting Gliese 887, which have not undergone many energetic explosions, may have retained their original atmosphere. What if I were to reveal to you that at least 2 exoplanets have been identified near this star. The first, Gliese 887b, is a super-Earth of about 4 Earth masses. It orbits its star in 9.3 days. Unfortunately, the small distance between it and its host, a little over 10 million kilometers, or 6.2 million miles, means that the temperature is far too high for water to be present in a liquid state. The second, Gliese 887c, is also a super-Earth, whose mass is estimated at 7 times that of the Earth. It orbits the star in 21.8 days. Do not rejoice too quickly, because unfortunately, for it too, the conditions are not optimal for it to harbor any form of life. Although a little further away from the star than the first described super-Earth, it is only 17 million kilometers or 11 million miles away. Once again, it is too close, and therefore too hot to maintain water in a liquid state, the temperature of its atmosphere having to reach at least 70 degrees Celsius, or 158 degrees Fahrenheit. However, any hope of finding an exoplanet in the habitable zone of Gliese 887 is not abandoned. Moreover, a candidate planet has been located in the habitable zone of this planetary system. Named Gliese 887d, this super-Earth of 8 Earth masses orbits its star in 50 days. Contrary to the 2 previous planets, it could therefore experience temperate temperatures and could therefore be well suited to the development of life. Another planetary system, also a little less than 11 light-years away, is located in the zodiacal constellation of Virgo. Let us now approach Ross 128, also named Gliese 447, the 13th closest star system to our Sun. This star has an apparent magnitude of 11.13. Its luminosity is therefore 100 times too low to be observed with the naked eye from our Earth. The primary object of the system is once again a red dwarf. Its mass is 15% of the solar mass, and its radius 21% of the Sun's. The temperature of its stellar atmosphere is 2,900 degrees Celsius, or 5,252 degrees Fahrenheit. Most of the energy radiated by the star is visible only in the infrared, with a luminosity 33,000 times lower than that of the Sun. As a result, it is of spectral type M4V, hence its typical cold orange-red color. Twice as old as our Sun, this star has been shining for over 9.4 billion years. Despite an entirely convective activity and a rotation speed considered slow, this flare star seems to have a long-term stellar activity cycle. As mentioned earlier, Ross 128 is part of a system. It hosts an exoplanet. This one, probably telluric, orbits in the interior edge of the zone of habitability, and thus receives approximately 38% more sunlight than the Earth. The planet Ross 128b is therefore potentially habitable. It is, after Proxima Centauri b, the second closest exoplanet to our solar system to enter this coveted category of cosmic objects. Let's see what this satellite looks like. Slightly more massive than Proxima Centauri b, Ross 128b contains at least 1.35 times the mass of the Earth. According to its hypothetical composition, if it is composed only of pure iron, it could have a diameter equivalent to half that of our Earth. According to the opposite hypothesis, if it is only composed of hydrogen and helium, it could then measure 3 times the size of the Earth. But considering that this planet could be telluric, its radius could be 1.1 times the Earth's radius, or about 7,000 kilometers or 4,350 miles, and its mass would then be 35% more massive than that of the Earth. Depending on its atmospheric component, its surface temperature could even be approximately the same as that of our Earth. Assuming that all these parameters are green, what about those related to the orbit of this planet? Ross 128b orbits rapidly around its star, in only 9.9 Earth days. This orbit is quite circular, thus having an eccentricity of only 0.036. It is more than 20 times closer to its host than the Earth is to the Sun, at a distance of 7.4 million kilometers, or 4.6 million miles. This proximity suggests that the planet has a gravity barely greater than that which we experience on Earth. But above all, it must always present the same face to its host. Apart from this particularity, this exoplanet is the only one known to date to resemble so closely our beautiful blue planet. But we must not lose sight of the fact that red dwarfs can be angry. Although the Olympian calm star Ross 128 seems to behave peacefully, it could have eroded the atmosphere surrounding the planet, evolving next to it in the past, during massive and repeated eruptions. But if this is not the case, if this star has always been peaceful, then Ross 128b could well be enveloped by an atmosphere. Why not welcome it? We could even go so far as to consider that it could already be home to one or more extraterrestrial life forms. Our interstellar journey is coming to an end. It has taken you almost 11 light-years from our Sun. You have been able to approach the star systems closest to our Earth. In this infinitely large space, an invaluable quantity of other systems remains to be discovered. Among those already listed, some are located at a short distance. Others, on the other hand, are several million light-years away. If for the majority of them, many similarities can be noted, for others one can distinguish an unusual composition. This is particularly the case for a system that is 150 light-years away from our galaxy, the system HD 98800, or TV Crateris. This one consists of 2 pairs of stars, distant from each other by 150 million kilometers or 93 million miles. I let you imagine what our sky would look like with 4 suns. But what makes it even more spectacular is the disk of dust that surrounds one of these 2 pairs. Another system, well known to all, also presents singular characteristics. It is Alpha Ursae Minoris, more often called Polaris. You know this star well under its common name of Polaris, easily spotted near the North Celestial Pole. It is the brightest star in the Little Dipper constellation. It is 431 light-years away from our Sun. But did you know that this star is in fact a multiple star? Polaris, which is a supergiant Cepheid variable, has in fact 2 smaller companions. It is thus a triple system. It has also been found 2 other components, even more distant. In the more or less distant future, future generations may be able to explore these even more distant star systems, where planets have already been found. This is notably the case for the TRAPPIST-1 system, located 40 light-years away. No less than 7 telluric exoplanets of the size of the Earth have been discovered there. 3 of them are in the habitable zone of the star. The observation of HR 8799, a star 135 light-years away, has also revealed another planetary system. 4 gas giants, 5 to 10 times the mass of Jupiter, orbit this star. But another system is in the sight of scientists. It is Kepler-22, located in the constellation Cygnus, 638 light-years from our Sun. A G5 main sequence star hosts an exoplanet named Kepler-22b. This exoplanet, twice the size of the Earth, orbits not only in the habitable zone of its host, but at a distance that provides a suitable climate for the water on its surface to remain in a liquid state. Back on our beautiful Earth, you can only become aware of the priceless treasure it offers us. The presence of life on a planet as we know it depends on so many parameters that it can finally seem like a miracle. However, the abysmal quantity of stars that populate the cosmos is enough to make us wonder. After all, if a solar system such as ours could be formed, why wouldn't there be others? Statistically, this simple theory is not far-fetched. This is what drives the astronomical community, always in search of new elements to understand the celestial mechanisms. Technological advances, which open the doors to future discoveries, will perhaps one day allow us to get to know new worlds. If so, how do you imagine